One of the motivating questions for section 2.5 is, can we use sort of a subset of a sequence to better understand its behavior? And that's what a subsequence is going to be defined to be. So we'll have to be careful about how we define that. But if you think about it, given a sequence, there are infinitely many values in that sequence. Is there a way to look at just a smaller subset of those values to determine what's happening? And one of the things that will come out of what we look at today in this video is a divergence criterion for showing that a sequence diverges. Right now, to show a sequence diverges, you would have to show that for any A, the sequence AN does not converge to A, and that could be a complicated argument. So is there a faster way to do this? So the first thing that we're going to need to do is give the definition of what we mean precisely when we talk about a subset of the terms. In particular, what is a subsequence of a given sequence? So here's the definition of a subsequence. So someone hands you a sequence A sub n, and then they're going to define a subsequence of A sub n, which we denote ANK. And that's given by essentially taking the original sequence AN and pulling terms from it in order, AN1, AN2, AN3, where N1 is less than N2, which is less than N3, etc., and just defining a new sequence. So we're creating sort of a subset of values. We're going down our sequence and we're saying, okay, I'm going to put A2 in my subsequence, and then I'm going to put A10 in my subsequence. So not all values of your sequence are going to make it into the subsequence. But one thing I want to point out here is that a subsequence is itself a sequence. So it still has to have infinitely many values in the list. And it's just a sequence of terms pulled from its parent sequence in order. So whose terms are pulled from its parent sequence. When I say parent sequence, I mean the original sequence A sub n in order. So to see what I mean, let's take a look at an example. So AN, if you think about how that's denoted, it consists of A1, A2, A3, all of these terms. I could define A and K to be A1, A4, A7, A10. Notice I'm picking every third term. That's one way that I might pull the values from my sequence. So just to put this in the context of the notation, let's figure out, I would pause your video and say, what's N1, what's N2, what's N3, what's N4. So pause your video, ask yourself, what should N1 be equal to? What is N2 equal to? Remember, these are the subscripts of the values in the subsequence. So N1 should be the value of the first subscript in my subsequence, which in this case is 1 because I've selected my first term to be A sub 1. Then my next value in the subsequence is A4, so that tells me that my second index, N2, is 4. My third index is 7, and my fourth index is 10. So NK is just a way of saying, well, what's the value of the kth index in my subsequence? So these values here are just the subscripts of the selected terms. So again, I'll point out a subsequence is itself a sequence. Think about times that we've heard this word where we'll have a term in mathematics and then we'll talk about sub of that term. So like a set, for example, and a subset. A subset is still a set. A vector space, you could have a subspace. Well, that's still a vector space. The reason why we say sub is because that's giving us reference to this larger global thing that's going on, that's letting us know that what we're dealing with sits inside some kind of larger structure, even though it still has the defining properties of the original term. Now, it's possible that you could take a subsequence of a subsequence. It's kind of silly, so you could be talking about sort of a subsequence. Facts about it, it's a subsequence of a subsequence of AN. And technically it's also a subsequence of AN itself. So you can think of the way you denote it would be ANKJ, and that's letting us know that we're going to pull, first we're going to go from AN down to ANK and only look at the terms in ANK, and then from that we're going to define a subsequence from that subset of values. So I could pick, A1, maybe I'll pick every other term, A1, A7, A13, etc. And here I would say that ANKJ is a subsequence of ANK, but it's technically also a subsequence of AN itself, because I could have just started with AN and pulled A1, A7, A13 and not used ANK as a middleman. So that's just something to talk about. We're not going to be working too much with subsequences, but they'll occasionally come up in this class, and so it's good for us to be familiar with the notation. So if we're going to be studying the convergence and divergence behavior of subsequences of some larger parent sequence, we want to have a good understanding of what the definition of subsequence convergence is. So what would it mean if I said that A and K converges to A? Well, remember, A and K is itself a sequence, so the definition of this should be really similar to the definition of just regular convergence. The only thing that's different here is that K is our value that's indexing our sequence. So note, K in the natural numbers indexes A and K. So choosing a tail is about considering K greater than or equal to capital N for some N. Now technically if you wanted, you could go with N sub K being greater than or equal to capital N. But if I wanted to write down the precise definition, it should be as follows. So A and K converges to A provided for all epsilon greater than 0, there exists a capital N in natural numbers, such that for all K, so K is the index of our subsequence, as long as K is greater than or equal to capital N, so that's telling me how many terms I should go out in my subsequence before I can guarantee that when I take A and K and look at its distance from A, it's less than epsilon. So again, this piece here, capital N is now going to be telling us a restriction on the index of the subsequence. So the tail is a restriction on the index of the subsequence. And some people might find this weird and they might prefer to work with just saying pick a tail such that little nk is greater than or equal to that tail. So one question that might be worth asking yourself is, how does little nk relate to k? Is there an inequality relationship? So we can go back to our original example up there. Remember when we said a and k was A1, A4, A7, A10. And we wrote out what these subscripts went with. So N1 was 1, N2 was 4, N3 was 7, and N4 was 10. So notice when I look at these, here in each of these problems, here I've got k is 1, whereas nk is equal to 1 as well. Here I have k is 2, the subscript on, because I'm talking about n2, so that's where I'm getting k equals 2 from, and then here's k is 3. And then this last one, k is 4. And so when I'm asking how does nk relate to k, I'm asking you to compare the values in this column with the values in this column. And so in general, what we see is we get this relationship that guarantees that little nk is always greater than or equal to k, because either you pick, when you're creating your subsequence, you're either picking every value in the parent sequence to be in that subsequence, or eventually you skip a value. And the moment you skip a value, the value of nk becomes strictly larger than k. So in general, nk is greater than or equal to k. So if you're restricting k to be greater than or equal to some tail, capital N, then nk will transitively also satisfy that restriction. So a first question in trying to understand how subsequences behave based on how the parent sequence is behaving is, well, what happens if we know that the parent sequence an is converging to some number a? What can you say about its subsequences? So I've drawn our standard picture here for showing a convergent sequence. So this blue sequence represents the sequence a sub n. It's converging to a. And I can chop my tail and guarantee that I'm in my epsilon neighborhood for the epsilon I've drawn, and for any epsilon for that matter. And I want to take a look at a subsequence of what I've given here. Well, a subsequence is just saying go through and highlight points on your sequence graph and put them in your subsequence, and just make sure that you have infinitely many of them so that you've created a sequence. So I'm just going to go down the line and I'm just going to randomly pick values. Maybe I'll pick every other one, doesn't matter. So maybe I'll skip this one and pick that one. So here I've highlighted some terms in pink. If I wanted to label these just for clarity, I would be saying that this is the value an1, here's the value an2, this one would be an3, an4, an5. Now, what can we say about what's going on with this subsequence, or any other way that I could have selected my subset? The high level behind what's going on is that the tail of any subsequence is just a subset of the tail of a sub n. So if I'm just working with the exact same tail, any subset of values pulled from that tail should still be inside my epsilon band, because all of the values in the tail are in the epsilon band. So high level, the tail of any subsequence of an is a subset of the tail of AN. So here my tail contains AN3, AN4, AN5, but that's just a subset of all my other values. And if I'm saying all the values are in the epsilon band, then any subset of them must also be in the epsilon band. So what we see is that we should expect that if a sequence is converging to A, then every subsequence should converge to A, because every tail of any subsequence that I generate is going to have to be intertwined as a subset of the tail of AN itself. So that's a theorem. I'm going to write that down. And this is a really important theorem. We're going to use it to develop a divergence criterion. We're also going to use it to prove one of the most important results in chapter 2, and that's going to give us a way to determine that a sequence converges without needing to know the value of its limit. Because right now we can only prove a sequence converges if we know what A is. Okay, so here's the theorem. If AN converges to A, then every subsequence is also such that ANK converges to A. So here we're saying for all ANK when I say every subsequence. Another way of thinking about that, if I was quantifying it, I'm saying for all ANK has to converge to A as well. So we were just noticing that in order to look at the tail of a subsequence, you're really just looking at a subset of the tail of the original. And so if you can figure out where to chop the tail of the parent sequence to demonstrate the parent sequence A sub n converges, then you can just use that exact same location to prove that your subsequence converges as well. So I'm going to go through the proof. Now keep in mind here, in this proof, we are proving the definition of subsequence convergence. So I'm going to be looking for a way to choose a restriction on my K values. So let's go ahead and write our proof. I get to assume AN converges to A. And now what I say next, everything that I'm introducing is for the sake of proving the logical structure of the definition of the subsequence ANK converging to A. So the first part of that definition is for all epsilon, which means I need to introduce an arbitrary epsilon value. So let epsilon be greater than 0. Now I'm looking for a place to chop my subsequence tail. And remember, we said where I want to do that is exactly the same place that I need to chop the tail for A sub n. So I want to introduce that tail now. So since AN converges to A, there exists a capital N in the natural numbers such that for all little n greater than or equal to capital N, AN minus A is less than epsilon in absolute value. So in particular, for all NK greater than or equal to capital N, those are exactly those values that are subsets. Those are my pink values that I've highlighted in my picture. Any value that's in my subsequence that's also greater than or equal to N is going to have to satisfy A and K minus A less than epsilon. But remember, technically we need to be talking about a constraint that's being placed on K itself, but we have a way to connect NK to K. That's what we were looking at earlier. We know that NK is always greater than or equal to K. So since NK is greater than or equal to K, it must be that for all k greater than or equal to n, a n k minus a is less than epsilon. If I make the restriction, if I say that little k has to be at least capital N, then that automatically guarantees that little nk is in the tail. And that's exactly what we want. Okay, now that we've proven this, I would like you to try to answer the following question. So we've just found out that when a sequence converges, all of its subsequences have to go to that same limit as well. So can you come up with a divergence criterion? A way to prove that a sequence A sub n has to diverge. Not just not converge to A, but diverge in general, in that sense that it's not going to converge to any real number. And I argue you can use the theorem that we just talked about to come up with this. So pause and think about that. So there are two ways that we can determine that a sequence diverges, and essentially we're going to be using kind of like the contrapositive of this last theorem. The first is that if an has a divergent subsequence, the moment it has a divergent subsequence, so that's a subsequence that doesn't converge to any value, that behavior is hidden inside an, and you can say, well, an is not going to converge to any value either, because you can just think of that subsequence as being the collection of outliers you're looking for to prove that. So first thing, provided an has a divergent subsequence, or there's another way this could happen. You could have that an has two subsequences that converge to different limits. This is very similar to what you've seen in calculus before, where if you wanted to show that a limit doesn't exist, you could show that from the limit from the left and the limit from the right are unequal. And then that would say the whole limit doesn't exist. Well, it turns out limits from calculus are built on limits of sequences. And so this divergence criterion is actually laying the foundation for that fact that you're familiar with from calculus. So we know that when a parent sequence converges to A, all subsequences have to go to A as well. So if I have one subsequence going to A and the other going to B, there's no way that I can converge to any set real number. So let's try to use this divergence criterion. Remember, we have this oscillating sequence, -1 to the n, and we've been saying all along that it diverges. Now, we've proven in the past that an doesn't converge to the specific value 1, but technically we haven't gone through the general argument to say that it doesn't converge to any number a, no matter what I pick for my limit. So we haven't yet proven precisely that an diverges. And that's what we're going to do now with the divergence criterion. So just a reminder about what the graph of this sequence looks like. It's just oscillating between -1 and 1. So here we're at -1, then we're up here at 1, then down here at -1 and up, and we're just going like that, back and forth. So I claim that this diverges, and I'm going to use the divergence criterion. So I would pause, think about how you would do this, and then come back and see the solution. So one thing we can notice here is that there's kind of these two subsequences of values that immediately jump out. If I take all of the even subscripts, then I'm going to always be picking up the value 1. But if I take all of the odd subscripts, I'm going to be picking up the value -1. So And those are constant sequences, which means that they have to converge. So consider the subsequence of the form. I'm going to call it, so I could say A and K if I want, but I can be a little bit more specific here. I could use the formula for how I'm going to choose my subscripts. So if I'm talking about all of the even subscripts, I'm talking about A to N. So that's going to give me all of the values that I get. So it's going to be like A2, A4, A6, A8. But those values are exactly the ones that come out as positive 1. And so then I'm also going to consider the odd sequence, or the odd subscripts. And those are going to be all the ones that evaluate to -1. And so to apply the divergence criterion, I just need to point out that these two sequences converge to different values. So since A to N converges to 1, but A to N plus 1 converges to -1, the divergence criterion implies that AN diverges. I've just found two subsequences that each converge to two different values. That's exactly the second condition of the divergence criterion. So that's a really simple way to do this. And we didn't have to do an epsilon argument. I didn't have to worry about varying A and coming up with my argument as I change the different limits that I say that my sequence is not converging to. So this is a much faster way to do it. But there's also another kind of question that comes up that we might be thinking about. You may have been thinking about it back when we were looking at the divergence criterion. We were talking about the existence of subsequences that either diverge or that converge to two different values. And that kind of begs the question, does every sequence have to have a convergent subsequence? So does every sequence have to have a convergent subsequence? So pause and think about it. It might help for you to start by thinking, first of all, you want to start by thinking about parent sequences that diverge. Because if they converge, then we know all the subsequences are going to converge. So we need to limit our class of sequences we're considering to ones that diverge. We have our prototypical examples of divergent sequences. We just took a look at one of them, -1 to the n, and we found that had two convergent subsequences. It actually has infinitely many if you are clever about how you pull your terms. But that leaves one other prototypical sequence to consider, and that's the sequence A sub n equals n. So what I'm going to point out here is that if we consider any monotonic unbounded sequence, it will have no convergent subsequences. And that's because if you begin as an increasing sequence, if you look at any subset of that, that's also increasing. And if you're going to have the original increase without bound, well, and the tails are intertwined, as we've seen, then that means that the tail of the subsequence is going to have to increase without bound as well. So I could look at an example. I could say use an to be n. All a and k are unbounded and increasing. Therefore, a and k diverges by the MCT. Now, this statement that I just made, I have asserted that any monotonic unbounded sequence will have no convergent subsequences. That is a loaded statement. It takes a little bit of work to show the details of this, and actually that's a problem I'm going to have you all try to do for homework. So here's another question. Does there exist an unbounded sequence with a convergent subsequence? So we just looked at an example of n where that's an unbounded sequence and it had no convergent subsequences. But is there a way to create an unbounded sequence that does have a convergent subsequence? And you may want to think about this graphically. So I would pause your video and try to come up with something. Once you see kind of what a graphical picture looks like, you might have an easier time coming up with an actual formula for the sequence. So remember that when a sequence is unbounded, it's because its values in the tail are trending off toward infinity. Any one value in the sequence has to be finite, and so if you're going to have overall unbounded behavior, you need to see that there's a place where a bunch of values are kind of going off to infinity. But you could do that in such a way that maybe you're, you pick your first term, and then your second term is just 0. And then you pick your third term and you increase, and then you come back down to 0, and then you go back up, and then you come back down to 0, and then you go back up. And so what I'm doing here is I'm sort of shuffling together a constant sequence, and then I could think of that as the sequence n if I want. So the answer to this question is yes. Whoa. Shuffle together an unbounded sequence and a convergent sequence. In that way, you're building a parent sequence that has to have the properties you want. So, for example, I could use an to be the sequence I've 1, 0, 2, 0, 3, 0, etc. And in this way, I get that a to n has to equal the constant sequence 0. So that converges to 0. But since a 2n minus 1, I'm using 2n minus 1 here instead of plus 1, just so that, because when I plug in 1 for n, that's going to give me a1. Otherwise, I'd be starting with 2, 3, etc. So I'm just making sure I'm including the first term. Doesn't matter, just being careful. But a2n minus 1 is equal to n, is unbounded. Overall, an must be unbounded. If you have a subset of values in your sequence that is unbounded, then that subset lives in the larger set. And so that means that the larger set can be proven to be unbounded as well, just using the same values that you use to prove the subsequence is unbounded. And one last thing that I want to highlight here from this example is that notice our technique for how we came up with it. We had these conditions we were looking to meet on our subsequences. We were looking for a convergent subsequence. We wanted our larger sequence to be unbounded. The way we did this was to, rather than thinking of a parent sequence and then checking if it does what we want, we instead built the whole sequence by starting with the subsequences we wanted that had the behavior we wanted and then shuffling them together. This is a really good way to think through construction of examples when you're asked to provide a sequence that has very specific properties. I recommend building it instead of just trying to arbitrarily try things and starting with the parent sequence and going down to a subsequence. So start with the subsequences and build up to the parent sequence instead.